necessary to put capacitor, then only we should do that. Okay. So now this is all about the logic gates. So now moving to CML D flip-flop. So in CML D flip-flop, generally not different kind of D flip-flops are designed. D flip-flop, different kind of flip-flops are not designed. Only D flip-flop is designed in CML mostly, and for that D type latch is designed first, and using two master and slave latch, the D flip-flop is implemented. Okay, so in this fashion, so you have clock and clock bar. Okay, so what you will do is you will concentrate on designing CML latch, and then by using two master slave latches, you can design a CML D flip-flop. And all the different circuitry, rather than different flip-flop SR, JK, all those we don't prefer. Only everything we will design using D flip-flop. Okay, so now again, because we have mux, so how to implement latch using mux? So again the same thing, you have select line, so you will apply clock in the place of select line, and when there is 0 in select line, then you will give A to the output, and when there is a 1, then you want to hold it. Okay, so you will connect output to the 1. Okay, so this is the logic of CML latch. So how to now design it? So first we implement a mux. So at the bottom, or we will apply clock and clock bar. Okay, and now let's assume this is A and A bar. Okay, and now the second input should be connected to the output. Okay, so that is why, and it is of opposite logic. Okay, so this is the output. So let me connect this and this first. Okay, and now you will connect here and you connect here, something like this. Okay, so this is the latch that we designed. So now maybe this looks like something different circuitry. So maybe if some of you have seen this circuitry, then it is in this form. Generally it is shown in this figure. So a positive feedback, and this is the CML latch. Okay, so when clock is on, the A is transferred to the output, and when clock bar is on, then this is a positive feedback. Okay, so the positive feedback will ensure that it will hold the value. So how it is positive feedback? So suppose this is high, so at that time this will be low, the output, because it is nothing but you can say that it is common source kind of structure. So if this voltage level at this node is high, here it will be low, and if this is low, node here is also low. If this is low, then this will be high. Okay, so again, if this is high, this will be high, so this is low. Okay, so whatever appear at the output, it will hold it, so it is a positive feedback. Okay, so in simplified version, if we try to put it, then we can actually represent this as a in this way. So let's assume there is some output load C1, and this is the I0, and this is R, and the other way is again a R, and this is off. So if this is off, then so at one time, if the C1 is charging, then at that time C2 will be discharging. If C2 is charging, at that time C1 will be discharging. Okay, because this is out 1, and this is V out 2. Okay, so when it is complementary, so it will result in this, and this V1 is can be either VDD or VDD minus IDR. Okay, so we know that this is either go to VDD or it will be VDD minus I0 or below it. Okay, so this is the swing. So I0R is the swing. Okay, so very quickly let me solve this. dt will be I0. Okay, and let's assume that V10 is initially VDD. Okay, so similarly, let's assume this is at V out 1 node. So V1T is VDD minus I0R 1 minus E minus T upon RC1. So all this thing is simple circuitry. So I think I should, rather than solving this, let me directly make it more intuitive in terms of waveform. Okay, so what exactly I want to convey here, that if suppose I have so let's assume that I have V out 1 that is going up. Okay, so at the same time the V out 2 will go down. Okay, so this is VDD, this is V out. Okay, so this is the operation of initial charging and discharging. Okay, so this is how it should go. But what will happen, that after certain T critical, okay, after certain T critical, if this is time, this positive feedback will be active. Okay, so it will not follow the same path that it should follow. It will go like this, and then suddenly positive feedback will appear and it will suddenly jump to 1, something like this. Similar thing will happen here. Okay, so rather than following this path, it will follow this path. Okay, and this happens because of positive feedback. Okay, and the time of latching is given by, so this is uh, before this time it is called sampling phase, and after this it is called regenerative phase. Okay, when the positive feedback is active. So first it is in sampling phase and then it will be in regenerative phase. Okay, and this regenerative phase, at this time you can, if you look this particular positive feedback carefully, it is nothing but it is a back-to-back inverter itself. So this is the very simple analogy that we can use for that. So it is like this. Okay, and if this is the simple analogy, if it, and if we will, so let's assume we have a load RL CL, and this is the simplified version of it, Vy. So this is first inverter and this is the second inverter, CL RL. So this is the small signal version of the same thing. Vx. Okay, so you can say it like this is one inverter and this is another inverter, and it is connected in back-to-back fashion. Okay, so this is the simplified version. So now if we write the equation for the same thing, it will be okay. So this will be the at this node, and at this node you can find, so if this is Vx and this is Vy, so this will be the equation. Okay, and we can further solve this, and if we assume that delta V is Vx minus Vy. Okay, so we want to see what, for what small change what will be the minimum voltage for, after that the latch will active. Okay, and that is delta V, so it is nothing but Vx minus Vy. Okay, and after solving this equation 1 and equation 2, actually we will get delta V delta V0 E AV minus 1 T by tau. Okay, and this tau is nothing but RL CL. Okay, so this by using this we can actually get tau latch, and it is tau AV minus 1, it is RL CL by AV is equal to CL by GM. Okay, and if we add the real component of the transistors, then GM is, let's assume some K2 factor GM. So this K2 mu n CUX W by L V effective. Okay, so we can say that T latch is nothing but CL by GM ln delta V logic divided by delta V 0. Okay, so if we want to improve the latch performance, we need to work on either GM, we need to increase the GM or reduce the load, okay, or we need to increase the input level. Okay, so this is the conclusion of this latch. So this is how we can actually improve the latch. So during design you need to take care of these parameters to get a better latch. Okay, and the latch is used in divider. So in PLL circuitry also we have seen that in PLL we need to have divider, and sometimes if it is high speed, then we need to have that divider in this CML form. Okay, so this particular latch will be used divider. So we know that if we want to have divider, so it will be Q, and this is Q bar, so we will apply Q bar to D. Okay, and here we have clock, so it will give you, this will give you F clock by 2. This is F clock. Okay, so this can, all thing can be implemented in CML logic. Okay, now there is another problem in the communication circuits. One is like your inverter is not sufficient to drive the load. Okay, suppose some CL is applied, but this is not sufficient to drive this load. So then what can be done? So in inverter CMOS logic, we know that what we do is we try to increase the size of the CMOS inverters, so that until and unless we can able to drive the CL load. Okay, similarly here also, in the place of CMOS we will use CML. So if we want to drive a higher capacity load, then we need to have you can say that CML which are consuming large current. Okay, so in circuit point of view, if we look, then this is R, this is R, and here we have applied B in, here we have AV in bar, and then if I is flowing here, then what we will do is so this is connected to current mirror. Okay, so I am not showing this, but this is connected to current mirror, and again similarly another differential kind of architecture, but this time the current will be K times larger. Okay, and that is why this is this W of these transistors will be K times larger, and the input of the output of this logic will be connected to the input, and the output will be taken from here. So this is R, this is R, this is out, this is out bar. Okay, so it is like, it is in the fashion like we have one, okay, because this is also buffer, and second is K times, in this fashion it is. Okay, so there are certain analyses. So here assume that because of the large size of transistor, the input resistance will be divided by K, and there will be some input capacitance. Okay, So now let's try to find the time constant. So time constant will be tau 1 plus tau 2. So tau 1 because of this r, and tau 2 will be because of the both of this resistance. Okay, so it will be rl cgd plus cdb and plus rl plus rg by k and kcgs plus 1 plus gmrl kcgd. Okay, so let me directly write the final thing. So gain is given by gmrl minus gmrl, and gm is nothing but I by v effective, we can say, and rl is also delta v by it. Okay, the swing divided by current. And so the gain, we can say that it is nothing but delta b by v effective. Okay, so very quickly let me come to the final equation so that we can conclude. It plus k plus rg by rl delta cgs plus 1 minus av cgd divided by it I total. Okay, so ultimately the purpose of showing this equation is that here you can see that we cannot work in most of the parameters here. Okay, so everything is kind of fixed. Okay, so the researcher has tried to find out the what can be the best possibility, or you can say that best current density that can be used. So over the different technology nodes, it was seen that the current density of 0.3 milliampere per micrometer, if this is used. Okay, so even if you will go lower node, there is no improvement in gate delay. Okay, so this is the rg which is telling you about the gate delay, but this gate delay will become constant after certain point. Okay, so this is constant over technology node for gate delay. Okay, so if this is constant over technology node, so that is the reason why you will see that in most of the recent paper in high speed circuit, this is they will design using this current density. All the circuit they design assuming that there is a constant 0.3 milliampere per micrometer current density, and they take it as a reference and design whole CML logic. So IDS is equal to 0.15 milliampere per micrometer minus VT. So this will scale with L. Okay, so this is about the CML logic. Now you can see that there is certain limit that we have achieved. So now there is you can say that there is less scope to improve the speed further. Okay, so because here everything is, if you take this 0.3 milliampere per micrometer, so you can say that the delay will remain the constant. The getting higher speed is relatively not that high that you expect in lower node technology. Then what can be done in CML logic? So from up to this point, all these are conventional kind of circuitry. But after that, if as a circuit designer you want to improve the circuit, then actually you need to go for different uh, circuit enhancement techniques, speed improvement techniques. Okay, so this is again a differential amplifier. So we can simplify this as a input, and this is voltage control current source, and we assume that this R is this R, and this is, there will be load, so this is the same load. Okay, so this is its small signal model, we can say. Okay, so in D flip-flop, if we want to further improve, so this is the D flip-flop now. So here you can see that this is master, this is the differential amplifier, this one, and this is the positive feedback, and this is master latch, and this is slave latch. So we reach up to a limit from above which we cannot go. Okay, so but there is a need of bandwidth enhancement. Then how to improve it? So there are various techniques. One is inductive picking and FT doubler and different things. So let's discuss some of them one by one. So before moving to the next speed improvement technique, okay, in next topic, where is speed improvement technique, I want to introduce a term that is called transit frequency. Okay, so the transit frequency is a measure of intrinsic speed of a transistor. So this is the speed which a transistor can achieve maximally when all the favorable conditions are provided to it. Okay, so let's assume I have applied a maximum power supply as a drain, as a gate, and took a minimum size transistor, and when I apply input in and take I out by in, then how much where it is crossing at zero, means when I out is equal to I in. Okay, that is the cross section point, and that cross section point will be the FT. Okay, so in graphical form also we will see. So in a small signal model you can see here that this is the transistor, and we have applied in. So generally this is only representation. Generally you apply V in simulation, you will apply V in and you can directly plot I out by in, and it is nothing but GM Z in. So ultimately when you put Z in here, that is J omega T C in, so you can say that okay, so your FT will be GM by CGS. Okay, so this is the maximum speed that transistor can have. So this is the small signal of the same thing. So we know that if we consider the capacitor also, so this is voltage control current source of for MOSFET. Okay, and this is the gate terminal, and this is drain, and this is source. So between gate and drain there will be a capacitance CGD. Between gate and source there will be capacitance CGS, and you will take I out by in. So here you can see that we need to look at only the green curve, this red one only showing the limitation of BGT. We for this particular circuit we don't need to look into it. So this blue one, if you see, navy blue, so you can see that it is constant for time, and this is the limit. So after which it will attenuate the signal and it is not usable. Okay, so this is called FT, transit frequency of a transistor. So this is the maximum speed. So for 180 nanometer CMOS technology, this is 60 gigahertz. Okay, but in 65 nanometer it is approximately 120 gigahertz. Okay, So you can maximum, this is the maximum speed that you can achieve using this technology node. Okay, but these numbers are also this is the maximum, but as you go for different operating region, so the speed will further reduce, and that reduce drastically. So even if the ft is 120 giga, ultimately at the last you will end up getting only 7, 8, 10 gig only. Okay, so now here you can see that ft depends on gm and cgs. Okay, so it is the transit frequency is the ratio of GM and CGS. So GM generally, if GM is constant, can we improve the FT using by reducing the CGS? Okay, so this is one of the way that what you do is you take two CML logic. Okay, so here you can see that here we have two differential amplifier. This is one differential amplifier. This is second differential amplifier, and you connect the two terminal, and Vin you apply at the other end of the differential amplifier, and this you will not apply any AC signal. Here you have bias it with some DC V bias. Okay, so ultimately what in differential amplifier we know that there will be uh, there will be ground. Okay, this particular virtual ground. So this node is virtual ground when there is V in. So if you have transistors in this fashion, okay, in this fashion, so if you apply V in plus and V in minus here, then this is virtual ground. Okay, but if your input is applied here and here, and this is connected, then this node will be the virtual ground. Now this is the middle point, so this is the virtual ground. So if this is the virtual ground, then this capacitor CGS, so now the this node will see two CGS in series like this, CGS1 and CGS2. So now if two CGS are in series, then overall CGS is CGS by 2. So the FT new will be GM by 2 pi CGS by 2. Okay, so by this way you can actually achieve 2 times FT. So double the speed. Okay, so by making a small modification in circuitry, but the disadvantage, there are disadvantage, like you actually end up burning double the power. But sometimes where you need a speed and there is technology limitation, then you think that okay, that is fine, we will burn more power, but at least we will get high speed. Okay, then another technique is inductive peaking. So in inductive peaking, what you will do is you will put our inductor in series with the resistor. Here you can see earlier we had only a resistor. Now an inductor is in series with the resistor. Okay, so if the small signal model we will see, this is the small signal model. Now this inductor is in series with the resistor. Okay, and when we take V out by V in, okay, we try to find the impedance here. So we get this equation. Okay, so this equation, if you look carefully, it is nothing but in the form of second order differential we have seen in control system, where you can actually improve the stability or peaking by varying the zeta. Okay, so here this is the simplified version. You can see that if you can actually vary the zeta and can get peaking at this particular frequency. Okay, so at the zoom version you can see that there is a variation here. So by varying the zeta you can get. So but for a stable operation you should operate for 0.5 to 0.9. Okay, and in general it is seen that approximately 1.6 times improvement in bandwidth we can achieve using this inductor load. But the disadvantage will be that you actually need to put inductor, and if you put inductor, then much of the area will be consumed by the inductor itself. And also you need to from output to the inductor you need to connect it by interconnects, and that will consume extra power. Okay, there is another way of doing the same thing, that is called inductive series peaking, where you will put inductor rather than in series with R, it will be in series with the load. Okay, in this fashion. Okay, here you can see both of the inductors. So ultimately again if we solve, this is what we get, and the same way as we did earlier you can actually play with zeta, and you can get the peaking. Okay, and as we have done shunt and series peaking, can we further improve the speed by connecting both? So sometimes this is also done, but again a huge area penalty will be there. But you will get approximately 2 times bandwidth improvement. So for example, sometimes you want speed rather than even if you want to consume more area. So for example, suppose you are working on 15 gigabit per second data rate, and by doing this by using this inductor you can go up to 25 gigabit per second to 30 gigabit per second data rate. So you will go to put these inductors so that you can achieve this much speed, because there is no other way. This can further be complicated using a transformer. Okay, so by using transformer, so it will be inductors in such a manner that and a capacitor in such a manner that it will form a star kind of inductor configuration. And if we further solve this, then we will get this, and again by adjusting the peaking you can actually improve the speed. So approximately 1.4 times we can achieve, and in theoretically it is saying that you can achieve up to 2.2 times bandwidth enhancement. Okay, but as I have told you that everything looks good in paper on paper, but if you actually go for designing inductors in layout, so here you can see that this is the buffer, and this is the inductor. So whole buffer comes in this much area, and inductor itself is taking too much area. Okay, so similarly this is one such example where inductors are used. Here you can see that these are the inductors, the circles, this inductor. So only 4 5 6 inductors are, means not more inductors are there, but many of the, you can say more area is consumed by inductor itself. Even the capacitor also very area consuming. Here you can see these are capacitors. Okay, so what can be the solution? So one of the solution of this problem is to use active inductor. So rather than putting actual inductor, you will make modification in the circuitry that it emulate inductors. Okay, so here you can see if we put a resistor with gate and drain in this manner, then if you solve this, you will get you can emulate the inductor. So if this is the impedance equation, where you can see R CGS plus 1 GM by CGS. So if you put S is equal to 0, so when I am saying that S is equal to 0, so I am talking about low frequency, so it will be 1 upon GMP. So here you can see, and when Z dot S is equal to infinity, then it is R. Okay, so this kind of characteristic we get. Okay, so, the emulated inductor value will be this. So by playing with CGS, GMP, R, all those, you actually we can play with the quality factor of the inductor. Okay, so let's understand the same thing intuitively. So this is the active inductor. So in active inductor, this is MOSFET. So this is voltage controlled current source GMVGS, and a CGS is connected between as with V with R in series. So now we know that what is the property of capacitor at low frequency. At low frequency, capacitor is open circuit. Okay, so when capacitor is open circuit, then we will get 1 upon GM as a impedance. Okay, if we look at from this side, and when we talk about high frequency, then this will be short circuited, and if this is short circuited, then we will get R as a impedance. Okay, so in general this R is higher, you can set that as compared to 1 upon GM. So this characteristic is something like this. So it emulates like a inductor characteristic impedance. Okay, so this is, and in simulation you can also see by varying the RG, actually you can get the peaking, inductive peaking. Okay, and so there are various such kind of methods that can be used. One of them is active feedback also, where you can use a negative feedback to get the active inductor. Okay, but uh, because of interest of time, I am stopping here itself. But you will find, if you look at gyrator, active inductor, or active feedback, all those are nothing but the emulation of inductor itself. Okay, and apart from that, there are various different techniques also, like capacitive degeneration, where you will put R and C at the source side, and there also you can get inductive kind of behavior. Okay, but it is called capacitive degeneration, negative impedance converter, and negative Miller capacitance. Okay, so these all are uh, speed enhancement technique that is used in CML logics. But mostly the capacitive degeneration and the active inductors are widely used. Okay, so with this I end this topic here itself. So if you have any question, you can ask.
Yeah. Thank you, Dr. Mahindra. Any questions from the participants? Please explain peaking waveform, PI.
Okay, so the picking, actually it is more related to the control system, you can say. So what will happen that in control system, if you just maybe let me move quickly to the, yeah, yeah, here. So this peaking is nothing but, so if you just go to time domain analysis of control system in second order equation, this is what you get. Okay, and in this, if you by varying the zeta, actually you can get this peaking. Okay, so you can control this zeta for different numbers. So generally it should be, the best value is called 0.707, but it is not always necessarily be put like in that value. It can be between 0.4 to 0.8. Okay, but by varying this, you can actually get this peaking.
Yeah, any other questions?
Hello, sir.
Yes.
Yeah, this one is a non-saturated logic, right? Very similar to ECL used in BJT. I mean,
Uh,
transistors never goes into saturation, right? Because your swing is very small, like 500 millivolt to 700 millivolt. So transistor never goes into deep saturation. So thus reducing the power consumption of the devices, right?
Actually, power consumption is not reduced because you can say static current will always flow there.
Okay,
Okay, so as compared to CMOS logic, definitely it will consume more power, but you will get benefit of high speed.
okay. But we can't get rid of the problem of inductor and capacitor, right? Since these components cannot be miniaturized at a larger extent in the on-chip application.
I have, yeah, so I have given you one of the solution like active inductor can be used,
Yeah,
but for capacitor also sometimes the MOSFET is used as a capacitor in some applications, but it depends on applications. In some of the places you cannot actually remove them, you need to put them.
okay, okay. And and one more thing actually, since inductor are already present in this circuit, inductor will, inductor itself will consume more power, right? It's a highly power consumption element, right? So current will
In
definitely charge up.
actually, yeah, but inductor actually inductor you can't say that inductor will take more power. It is like that you need to drive the inductor that will so your buffer stage will take more power.
Okay. Yeah, we have to trigger the inductor or to drive the inductor to a high power, right? To charge up
Yeah.
the element. Okay, okay. And what is the maximum operating frequency of this circuit?
Actually, I whatever circuit I have shown that is generalized one,
Okay,
but up to 20 gigabit per second we have got in simulations.
okay, 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 okay. Thank you.